In this video, we're going to talk about the geometric and negative binomial functions. Let's begin with the geometric function. Up here you see the density function, which has one parameter, p, otherwise there is just the data, and the cumulative distribution. As with other videos, I have provided a column full of x values, and I have used the density function to calculate density values. In this instance, I am using a probability of 0.3 to calculate the density values. Because this is a discrete distribution, these values, the fx values, are the actual probabilities of the outcomes that you see. With the binomial distribution, we fix the number of trials, n, and let the number of successes vary. For example, suppose we play 10 games so that n equals 10. In the binomial distribution, we ask what's the probability of winning 1 game, 2 games, no games, 3 games, all the way up to 10 games. But suppose instead we held the number of successes to 1 and let the number of trials vary. In other words, how many games must we lose before we get 1 win? If the probability of success is constant, then the random number x of unsuccessful trials required to obtain the first success has a geometric distribution with parameter p. So let's have a look at this. Over here we ask how many games will we lose before we get 1 win. Let's pull up that distribution. You'll see it's the one that is embedded in the file here. This is a geometric distribution. It has a probability of 0.5. You'll see the most common outcome is there will be no losses before you get a win. That'll be a 50-50 proposition, as you would expect. Then the most likely outcome is there would be 1 loss before a win, 2 losses before a win, and so on. You could see it would be highly unusual that we would lose, for example, 8 games before we get our first win if the probability of winning any game is 50%. We can, of course, change this. Perhaps if we were the dominant team, we would see that most likely there are going to be no losses if we have a 90% chance of winning. Or if they are the dominant team, you could see that there is a good likelihood that we could lose many games before we get our first win. But let's go back to the 0.5. Close this now. And you can see as we hit the F9, here is an example where it took 4 games, 4 losses to get the first win. 1 loss, 1 loss, 1 loss again, 0 losses, 0 losses, 0 losses again, 0 losses, 1 loss, and so it would go. The value returned by the at-risk distribution represents the number of failures prior to a success on a series of independent trials. There's a probability of success of p on each trial. In the example we've been talking about, p is equal to 0.5. The geometric distribution is a discrete distribution, and it returns only integer values greater than or equal to 0. This distribution corresponds to the uncertainty about the number of trials of a binomial distribution that would be required for an event of given probability to occur for the first time. Examples would include the distribution for the number of animals you'd need to test to find a diseased animal when the incidence of disease is p. It could include the number of smartphones that you produce or purchase before you come across one that does not work when the defect rate is p. It could be the number of lockages at a lock before a stall occurs when the probability of a stall is p. The distribution can also be used in basic maintenance modeling, for example, to represent the number of months before a car breaks down. But remember, since this distribution requires a constant probability of breakdown per trial, other models are sometimes used when the probability of breakdown increases with age, or if it would decrease with age. Now let's move to the negative binomial. Suppose we're interested in the number of trials required to reach some number of successes that's larger than 1. To do that, we need a negative binomial distribution. This has the parameter p, and it also has the parameter s, the number of successes. So if we stick with our baseball example, or our ball game example here, if the probability of winning one game is 0.5 and we want 3 wins, we want to know how many games will it take, how many unsuccessful games, how many losses will it take for us to get 6 wins. And of course the answer is we don't know, because there's variability in the world. If I pull up this distribution, however, you'll see it's reading the probability and the number of successes from the spreadsheet here. And so this is a picture of what the outcome is likely to be. Most likely you would lose 1 or 2 games before you won 3. But you see the 3, 4, 5, 6, 7, and so on all still have a non-trivial probability of occurring. And so here, when I hit the recalculate button, this would be one experiment. Took 3 games to get 3 losses before we got 3 wins. If I hit F9 this time, it took 4 losses before we got the 3 wins. I hit F9 this time, it took 1 loss before we got to 3. And so it would go. If you change either the probability of winning, let's make that a 0.1 where the other team is dominant. Now you see it would take quite a few games before we could get 3 wins. And the distribution looks quite different now. The negative binomial distribution is a discrete distribution that returns only integer values greater than or equal to 0. The distribution represents the number of failures before several successes of a binomial distribution have occurred. So that if we have a negative binomial with 1 success and a probability of p, that's exactly the same as the geometric distribution we were just looking at. The negative binomial is sometimes used in models of quality control and production testing, as well as breakdown and maintenance modeling.